the world of information technology, everybody seems to want something smaller and more reliable. And if possible, they would like more features and a reduced price. The manufacturers want to make products for as little as possible, and with development costs for high-tech products being so large, the manufacturers would prefer to build their product in a form that their competitors can't copy. Now, if you're pretty certain that you're going to sell tens of thousands of products, say like this Speak and Spell, then the answer for some time has been to turn your original design of many individual components into just a couple of custom chips, and this is what these 3 chips are here. But custom chips are expensive and they take a long time to produce. So Microlife has been looking at a new way of making these custom chips. We followed the story of one particular chip designed to work with Acorn's BBC Master Computer. Acorn were developing a product for use in an interactive video disc system. Now, the present BBC machine offers 8 standard colours, there they are, and one of the things that the manufacturers wanted to do was to widen the range of colours available. Well, we convinced Acorn to try a new process and have some of the electronic circuitry needed for this development customised onto a single chip.
We went to Texas Instruments in Bedford to find out what lay behind the process. How can customising simplify a design like this?
Well, if we take a circuit such as Acorn's video processing unit here, you'll see the traditional way a circuit would be designed is as a number of building blocks. Each one of these being an integrated circuit with a number of components within it. These range from simple logic functions through to memory elements. Customising allows us to put a number of different functions all on a single chip. And in the example here, we're replacing about 15 of these chips.
Right, with just the one?
With just the single device.
Turning those 15 chips into one is easier said than done. Believe it or not, you would need this lot. That's about 15,000 components to build up the functions we're expecting of our one custom chip. To begin the chip design, the circuit details are entered into a workstation. This is done component by component, with each connection defined by a line of text. Or, in an alternative form, pictorially, giving a direct match with that original circuit diagram. Once the design is entered, TI now relies mainly on workstation software to do the rest. It checks the entire circuit for entry errors by simulating the circuit's performance. The software feeds in known inputs. The outputs can then be checked against the waveforms expected from the circuit. When Acorn's circuit is turned into a custom chip like this, it will still be made up of those thousands of components, because the chip is just a very large number of tightly packed transistors, resistors and so on. So this design must still be converted into a component design, and this into areas on the silicon slice which will act as tiny transistors, resistors and so on, which when interwoven together make up the working chip. These components are sculpted onto areas on the surface of the silicon slice. These areas, traditionally created using masks, are defined by exposing slice and mask to ultraviolet light. Each exposed area fixes where chemicals are to be diffused into and grown onto the surface. The final chip is made by repeating these steps many times with different chemicals. To design the chip's physical layout, it's back to that workstation, where hardware and software do the hard work once again. Each one of these tracks, drawn here in green, will be no more than 10,000ths of an inch wide on the final chip. The green here stands for aluminium conductor. The yellow areas for one type of diffused chemical, a semiconductor region. And each of the other colors stands for a different chemical layer on the chip's surface. Software now not only draws in these interconnecting layers, but also checks out its own designs for mistakes. Before the arrival of this software, many of these design stages were, until pretty recently, carried out manually. Now, all this workstation software must have replaced a lot of skillful engineers.
Not at all. Those skillful engineers are now designing at one level higher than they have been used to. The analogy is clear if we go back 15 years. In the late 60s, many engineers were designing at the transistor level. In the 70s, the advent of custom logic functions, which each of which perhaps mopped up 100 transistors, allowed the designers to build more complex systems in the same amount of time. We've now just gone one stage further, allowing designers to build with the higher level building blocks.
So much for design. Chip manufacture calls for exacting conditions and some pretty strange garb. The many interacting layers which go to make up the chip have to be very accurately superimposed one on top of the other. Until recently, the only way of doing this was with these photographic masks. It required a lot of exotic equipment. Costs quickly mount up when each mask can cost around £1,000 to make, and when each chip needs between 10 and 15 masks for its manufacture. TI, though, are now using this electron or E-Beam technology to write directly to the surface of the chip, and that avoids the need for these expensive masks. The data from the design operation is fed into the E-Beam system. A fast computer working at effectively 50 million instructions per second then drives the system from this data. The silicon slice, covered in a material sensitive to an electron beam, loads into a vacuum chamber. It must be accurately aligned before the electron beam is driven across its surface. The beam scans the surface, exposing areas of the slice. In this way, the areas for later chemical deposit are marked onto the chip's surface. This E-beam scanning process is carried out to an amazing accuracy. In fact, that beam is deflected to within 10 millionths of an inch, which is about the length your fingernail has grown in the last minute. What does E-beam have to offer over traditional customizing to your customers?
Well, there are two key advantages. The first is that customers can now consider and can afford to have much lower volumes than traditionally available with custom design techniques. It's now feasible to have volumes as low as just 1,000 pieces, whereas in the past, due to the excessive cost of the photomask approach, they would have required many tens of thousands to justify the overall cost of the project. But secondly, the processing is now extremely fast, with E-beam at every stage. The time taken to start from raw silicon and end up with custom chips is a matter of just 1 or 2 weeks.
John, thank you very much.
And this is it, the MicroLive chip. The cost advantages of producing a chip in this way are very interesting. Using conventional mask techniques, the initial costs are very high, although they do come down eventually with volume production. But many UK producers don't want that sort of volume, so they can't take advantage of the reduced price. But with the E-beam technology, the starting cost is much less, and low-volume production becomes a realistic proposition, putting custom chips within the reach of many manufacturers who previously considered them too exotic. Well, the other advantage is obvious. Now, this is the board with the non-custom design, and as you can see, there are so many bits and pieces on it that they've had to actually go up another story to get everything on. And then next to it is the board with the custom chip on. There it is, and you can see how much neater the layout is. Well, Acorn have great hopes for the growth of the video disc market, and now they have a cheaper chip, a neater box, and something which the opposition should find difficult to copy.
Last year, Sir Clive Sinclair sold his